Hi there. Welcome to this lecture series on matrix algebra. This is lecture 15, part 2. The topic is orthonormal basis. In this part of the lecture, we'll cover several more examples using the Gram-Schmidt algorithm, and we will cover orthogonal matrices as well. Okay, let's get started. We now give an example where the vector space is of continuous functions. So let now V be the space of all continuous functions defined on the interval from -1 to 1 and associated with the inner product. So FG inner product between them with this notation here would be the integral from -1 to 1 of fx times gx dx. And now we consider a subspace which we call W. The subspace is all functions px, which is a plus bx plus cx squared for a, b, c real numbers. So this will be a space of all polynomials of degree less than equal to 2. And the goal for this example would be finding an orthonormal basis of W. Okay, so let's look again at the definition of the space W. And as first step, let's try to find just a basis. So we see this is polynomial of degree less than equal to 2. And in this general expression, we see that there are 3 coefficients, and then they are multiplying onto 3 functions. First one is 1, the second is x, and the third is x squared. So we can define these 3 functions as P1, P2, and P3. Okay, and then the space W would be the span of P1, P2, and P3. So these 3 functions, P1, P2, P3, they are linearly independent, but however, they are not an orthogonal, and they are not with the norm 1. So the goal here would be starting from this basis that we have here, and we want to construct a new basis. Let's call these 3 functions Q1, Q2, and Q3, such that the polynomials Q1, Q2, Q3 will have norm 1, and they are perpendicular to each other. So to solve this problem, we can simply follow the Gram-Schmidt algorithm and replacing the vector there with our functions and replacing the vector inner product with the inner product for functions, that is the integral function. Okay, so let's start. Step 1, we will first let's compute the norm of P1, which is P1. So P1 norm squared would be inner product P1 with itself, and that's the integral from -1 to 1 of 1 times 1, which is 1, and this integral is 2. Therefore, the norm of P1 would be square root of 2. Okay, and then we can use that to normalize the P vector and get P1 vector, and then we get our Q1. So Q1 will simply be the P1 divided by the norm of P1, which will be 1 over square root of 2. So this means this is a function identically equal to this number 1 over square root of 2 for all the x values. Okay, so one can easily verify that the norm of Q1 would be 1. So you can take Q1 inner product with itself, and this one inner product with itself will get you half, and integrate half over the interval from -1 to 1. You will get 1. Okay, step 2. First step in step 2 is to compute this Q2 tilde, which is a vector which equals P2 minus the perpendicular projection of P2 into the space formed by span of Q1. So this is the formula. And well, now let's plug in. So now P2 is a function, it's x, and then we calculate P2 dot Q1, and which is the integral from -1 to 1 of x times Q1 is 1 over square root of 2. Okay, so and dx. So this will be a function in the end. And then Q1 is 1 over square root of 2. So if you work out the integral and you see that this gives you 0, so you just have x. And the next step would be to normalize Q2 tilde. So let's compute its norm first. So the norm square is the inner product. And let's do the inner product. So integrate from -1 to 1 of this times itself. So it's x squared dx. And that's just integration of x squared, which is easy to find. And we get 2 over 3. Okay, now we can normalize Q2 tilde and find a normal vector Q2 by dividing Q2 tilde with the norm of Q2, which is square root of that one, and Q2 of x is tilde of x is x. So now the normalized function here is this one, and you can go ahead and verify that Q2 will have norm equal 1. So let's take a pause to see what we have achieved so far. So we see now we have constructed 2 polynomials, Q1, which we have, and Q2, it looks like that. And then we also have that the span of Q1 and Q2 is the span of P1 and P2. They are the same. And what is P1, P2? Which is 1x, right? And furthermore, Q1, Q2 is an orthonormal basis of this subspace span of 1 and x. That is, this will be the subspace of all polynomials of degree less than equal to 1. Okay, so we have one more function, and let's take the step 3. So P3 is x squared. And then we can define Q3 tilde to be P3 minus a perpendicular projection of P3 onto the span of Q1, Q2. Okay, and this gives us P3 minus this formula here. So it's a linear combination of Q1 and Q2 with the coefficients. That's the inner product of P3 with Q1 in front of Q1 and P3 with Q2 in front of Q2. So the rest is to plug in all these functions are given, plug in and work out. All right, let's plug in. So P3 is x squared, and then P3 inner product Q1 is the integral of the product of these two, and then Q1 is 1 over root 2 minus inner product P3 Q2. So that's P3 and that's Q2, and that's the inner product, and then Q2 is x over root of 2 over 3. So these are just all integrals of polynomials with coefficients, and integrating from -1 to 1, one can easily work out. Okay, so if you work out and then you see that, and you will get x squared minus 1/3. And finally, we need to normalize the Q3 tilde. So we compute the norm. We find the norm square by computing the inner product, which is here. And x squared minus 1/3 multiplied by itself, it becomes a polynomial of degree 4. You can expand it and write out, and this is what you will get. And then you can integrate each term and evaluate from -1 to 1, and that's what you will get. And you add them all up, you get 8 over 45. Okay, so the norm of Q3 tilde will be square root of that, and then you can use it to normalize the Q3 tilde, and you get Q3, which is now a vector, a function of norm 1. So it's Q3 tilde divided by the norm, which we just computed here. So you can write the inverse here and make it into a multiplication. Okay, so then we completed this example. Okay, so now let's summarize what we have shown through this example. It says now the three polynomials Q1, which is a constant, and Q2, which is a polynomial of degree 1, and Q3, which is a polynomial of degree 2, written in this special form. They provide an orthonormal basis of the space W of all polynomials of degree less than equal 2, with the given inner product, that is fg inner product is the integral of f times g from -1 to 1 dx. Okay, so what does it mean is that these three functions, polynomials Q1, Q2, Q3, satisfies this relation, that is the inner product of Qi with Qj would be 1 if I is j, meaning the Q inner product itself gives you 1, and it's 0 if I is different from j, meaning two different functions from this set will have inner product 0, and therefore they are perpendicular. So a word of warning before we proceed is that for this space of functions, and everything depends on the inner product. The basis here we have as Q1, Q2, Q3 would not be orthonormal basis if we change the inner product. For example, instead of taking the inner product from -1 to 1, if we define an inner product from 0 to 1, then you can carry out the Gram-Schmidt algorithm and you will get a very different result. Okay, so let's talk about approximating a function by a polynomial. So polynomials are very important functions in many applications, and therefore there is a common task that we need to perform in many analyses is to approximate some complicated looking function with a polynomial, because a polynomial you can easily differentiate, integrate, and do many things to it. Okay, so here's the setting of the problems. Given a function y, some function, and then we want to find a linear polynomial px, which is ax plus b, represented by this way for a and b to be scalar numbers, and we want to find it that it best approximates the function f. Okay, so then you need to be specific of what do you mean. So first, and we need to specify what interval are we seeking this approximation, and what do we mean by best. Okay, so and let's take a look at some example just graphically. So let's say if we ask where do you want this best approximation, let's say if we want it to be just at a point and a very small neighborhood around it, then your best approximation of this function in that tiny segment would be the tangent line. Okay, that is the line that touches the graph of f of x at the point x0. And second, let's say we want to approximate it on the interval from 0 to 1. So I don't care about how f looks outside, but on this interval, I want to approximate it by a polynomial of degree 1 as best as I can. So you know if f is bending, then it will not equal to a polynomial of degree 1. So you would intuitively think that the plot of the polynomial, the straight line, would cut through f and leave some part of the f above the line and some part below. So kind of evenly distributing the arrow. We haven't defined it yet, but roughly speaking, so that they become small, right? And third example, if I want it to have a best approximation on the interval from -1 to 1, then I will enlarge my interval and carry out a similar analysis we've done here. Find a straight line that kind of intersects the f function so that the area above is kind of approximately the area below, so the arrow is small. Okay, let's look into some details. Okay, so let's consider the case we want to find the best approximation over the interval from 0 to 1. Then we can specify what is the arrow. So we want to find a function ax plus b with a and b to be the unknown, such that the integral from 0 to 1 of fx minus this p of x here and the square of that dx is as small as possible. Okay, so we recognize that this is the inner product of this function with itself. Okay, and then from the discussion we have had, we realize that this is the same problem as the following. That is, find the perpendicular projection of f on the subspace and where this function would be in, that is w is span of 1 and x, where it's also like the function of polynomials of degree less than or equal to 1. So all p of x equal ax plus b, where a, b are real numbers. And the inner product, because you need the inner product to define the perpendicular projection. Okay, so the inner product is the integral from 0 to 1 of f times g dx. So pay attention here, the inner product, the integral, the upper and lower limit must be the same as the integral here where you calculate the arrow. And we see this is a problem we know how to do. And next, let's look at the best approximation over the interval from -1 to 1. Then it's very similar, except that when we try to minimizing the problem, the minimization will be over this integral from -1 to 1 of that whole interval. Then this is totally similar to the previous part, which we will just need to replace the interval into an integral from -1 to 1. Otherwise, this looks just the same. Okay, and this calculation, we know, we have learned already how to do that. Okay, so the last topic we'll cover here is something called the orthogonal matrices. So the definition is the following. We say that an n by n matrix, so it has to be a square matrix here. And this matrix A, we call it an orthogonal matrix if it satisfies the following. That is, its transpose coincides with its inverse, meaning A transpose equaled A inverse. Okay, if that holds, then this is a orthogonal matrix. Okay, so if the A transpose is A inverse, then you can have the identity A transpose times A, which is just A inverse times A, which will give you the identity matrix. Let's write out this identity here using the column vectors of A. So if I write A as column vector, we call them V1, V2, all the way to Vn, there are n of them. Then the A transpose, you can utilize these same column vector and they will become the row vector of A. So you will have V1 transposed, V2 transposed. These will be the row vectors all the way to Vn transposed. And this will form the A transpose. And then this product will give you the identity matrix, which means that the diagonals will all be 1 and everywhere else it's 0. So we see that if A is an orthogonal matrix, that is, this identity holds in that case, then we see we have the following. Each element here can be computed as the inner product of this V times this row, the certain row here times the certain column here, right? So we will see Vi dot Vj, the inner product, will be the Vi transpose times Vj. And then if A is orthogonal, then we know that it equals 1 when I is j, and it equals 0 when I is different from j. So we see that if A is an orthogonal matrix, then we have this property for the column vectors, and this is exactly the property for an orthonormal basis. So the column vectors of A actually now is an orthonormal basis for Rn. Now let's look at one important theorem regarding the orthogonal matrix. So if A is orthogonal matrix, then for every vector x in Rn, and if you multiply it, if you do the product A times x, then you have a vector that has the same length, which is, in formula, that means the norm of x equal to the norm of A times x. Okay, so the norm is the length of this vector. Okay, let's do a quick proof. So we aim at proving that the square of the left equal to the square of the right of this identity here. So ax norm square would be the inner product of ax with ax, and then it is ax transpose times ax. So we're going to apply the rule of the transpose of the product into the product of the transpose, but in the reverse order. So this transpose will be x transpose times A transpose. We switch the order times that. And then now we have this multiplication, and we know that we can, if we keep the order as is, and we can do certain parts first. So we can do the A transpose times A first, and then multiply it to the vectors on the left and right. Okay, and then we have A transpose times A, which is the identity matrix, which doesn't change the result, so it just becomes xt times x. And this is exactly the x norm square. Okay, so we proved it. Okay, so so this has meaning in a linear transformation. So we discussed earlier about linear transformation. Let's say every linear transformation can be written as an A matrix times an x vector. Okay, so this property means that a linear transformation respects the norm or preserves the norm when A is an orthogonal matrix. So if you take a vector x and you transform it, and you get another vector A times x, it will have the same length. Let's take a look at an example for a special matrix in R2, which we looked at earlier. Let's call this Q matrix, which is cosine theta negative sine theta and sine theta cosine theta. And you can go ahead and verify that this is an orthogonal matrix by definition. Okay, so we first identify the two column vectors v1 and v2. v1 is the first column and v2 is the second column. Okay, and we perform the inner product. v1 dot v1 and would be cosine square plus sine square, which is 1. v2 dot v2 is sine square plus cosine square is 1. And then v1 dot v2 is negative of the product and then positive of the product, and it's 0. Okay, so this shows that v1, v2 are orthonormal vectors, and therefore this matrix Q here is an orthogonal matrix. And now we can consider the map from X to QX, applying a 2 by 2 matrix multiplying onto a vector in R2. So in our earlier discussion, we have found that this map here describes a rotation of an angle theta. So more specifically, if you have like a little square area in the x1, x2 coordinate, and then after the transformation, it is just a rotation. So the vector here becomes the vector here, and the vector here becomes the vector here, and it's we call it a rigid body rotation. You simply rotate it without distorting anything of it. So these vectors will have the same length as the vector in the x coordinate. Okay. So that is due to the fact that an orthogonal matrix respect the norm. Okay, so that's all for today's lecture, and next time we will looking into something called the least square method. Okay, so I hope you enjoyed this one, and I'll see you next time.